Well, we're going to discuss developing fraction operations, part one, based out of chapter 15 in John Van de Waal's text, Elementary and Middle School Mathematics. Hope you enjoyed a little humor here in the front slide with the cartoon. But let's talk about what the goal of this video is going to be today. We're going to start with a little review of some fraction concepts from our last video, just to set the stage for today's lesson. And then our main goal today is to unpack addition and subtraction with fractions, thinking about developing different meanings for making sense of these operations, and then leading towards developing algorithms to be efficient computationally with addition and subtraction of fractions. So those will be our three goals. So let's get started. All right. Well, one thing from the last video, it's an important idea, is the three different types of fraction models that we can use. On this sample workbook page, we see students are asked to represent the fraction 3/5 in several different ways. And as you may recall, we see the top left and the bottom right. We have two different area models in terms of shapes, partitioned, rectangles and circles. In the top right, we see a length model looking at what it would look like on a number line. And the bottom left with the stars, we call it a set model, just looking at individual objects and thinking of fractions as in, for example, 3 out of 5 stars, 3/5 of the group. And so today, as we work with addition and subtraction of fractions, let's often think about it in terms of these three different models: area, length, and set. Another big idea from the last video was just the idea of equivalent fractions, that as students reasoned about fractions in grades like third grade and going forward, a big idea was trying to understand that there's many ways to name the same fraction. And here we see a third grade standard from the Common Core that says that. Recognize and generate simple equivalent fractions, for example, like 1/2 equals 2/4 and so on, and explain why the fractions are equivalent by using a visual fraction model. So for example, here with the fraction tiles, we could take these out and explore different types of equivalent fractions, seeing all the different ways we could make, for example, 1/2. We might realize that it's the same as 2 of the 4ths, or 3 of the 6th, 4 of the 8ths, 5 of the 10ths, 6 of the 12ths, and all of those are equivalent. And a big idea in fraction operations is this notion of equivalent fractions. So important to get the different ways to name the same fraction. One thing you may have seen in certain curricula, which is interesting, is the idea of finding equivalent fractions using the giant 1. And let me just show what this looks like for a second. I'm going to pull up my document camera here. And as we look at the fractions like in the last with the fraction tiles, and we saw that 1/2 was the same as 2 of the 4th pieces, or 3 of the 6th pieces, or 4 of the 8th pieces. Of course, we start to see patterns. For example, that if we multiply the 1 by 2 and the 2 by 2, we get this one. And for example, if we multiplied 1 by 3 and 2 by 3, we get that one. And we start to see a little bit of a simple algorithm to write equivalent fractions. But what's happening here? And why do some curricula call this multiplying by the giant 1? Well, we know in math that anything times 1 is itself. For example, if I took 1/2 and multiply it by the number 1, we know the answer would have to be 1/2, right? Multiplying by 1 doesn't change anything. It's the multiplicative identity. So there's lots of creative ways to write the number 1. And some curricula, what they do is they actually write kind of a giant 1 to emphasize this. And if we wanted to find an equivalent fraction for 1/2, well, we can choose any fraction that equals 1, like 2 over 2, 3 over 3. Let's choose, how about 4 over 4? 4/4 we know is 1. So I'm putting it in the giant 1 just to emphasize that that fraction just equals 1. So we know the answer has to be 1/2. Well, when we multiply across, which does work as we'd expect, as our intuition might guess at first, we get 4/8, which is the same as 1/2. And this is, of course, they are equivalent. They're the same thing. And the giant 1 ends up being just a little tool that some curricula use to find, I'm sorry. In this case, it would be 5/10. We know that then that is the same as 1/2. So interesting, just a little note on equivalent fractions that may come up a little bit later. But let me come back here and we'll carry on. The other big idea from the video last week was just reasoning with fractions. We talked about lots of ways for students to reason about size of fractions and comparing fractions and going through. And one interesting idea using a length model example is the idea of reasoning with interactive number lines. one interesting activity that's kind of swept over a lot of classrooms these few years is taking a simple string or rope and tying it across, and in this case, using cards like the orange benchmarks of 0, 1/2, and 1, and giving kids cards for fractions and trying to ask them to place it where it would be on the number line and have the class engage in discussion and debate of where they would be. Of course, the green cards here are not in the right places, so we have to talk about it. Where would 1/10 go? Would that be to the right of 1/2, to the left of 1/2, closer to 0, closer to 1/2? These are the kind of questions and reasoning skills that we talked about last week just to build relative size of fractions to going through. So all of that will be kind of important as we think about this first video of developing strategies for fraction computation. So let's dive in. So, true story. Many years ago, when one of my daughters was 10 and she was doing some math homework, she came to me and said, "Dad, fractions are hard. Can you help me? I forget how to do 5/8 plus 5/8. Well, question, what would you do? Maybe pause the video for a moment and just think, well, how would you answer that question? How do you make sense of 5/8 plus 5/8? Well, looking at a national report on teaching of mathematics, there was 4 key ideas that this report had about helping young learners understand fractions deeply, and here were their 4 suggestions. Number 1, they said, well, turn it into a contextual story problem. I mean, what does 5/8 plus 5/8 even mean, right? So we need to think about putting it into a context that learners can understand. Number 2, think about estimating the answer. And I'm not saying estimate like exactly, but just the idea of, do you think our answer is more than 1 or less than 1 or more than 2? And we'll talk about why that's important in a bit. 3, use visuals. Explore using models, pictures, manipulatives, things that make sense of it. And 4, there's a lot of potential misconceptions with fractions, so let's address those explicitly and be intentional about talking about why things don't work maybe the way we think they would. So let's take a look at that same situation and take a look at some ways we might go through these steps and think about this with my daughter's question of 5/8 plus 5/8. So to do that, I'm going to take a look at a virtual manipulative here, and let's go back to my screen. I'm going to pull up a page from Mathigon that has some nice fraction tiles. I'll give you a link to these later. But let's think about what 5/8 plus 5/8 means. Well, first of all, we need a context, right? So for example, let's say that on Monday, I ran 5/8 of a mile in my great workout, and on Tuesday, I ran 5/8 of another mile. So a question might be, well, how far total have I run across those 2 days, right? So starting there, even that context can give us something to sink our teeth into. 5/8 of a mile on Monday, I ran 5/8 of a mile on Tuesday, so how many total miles have I run? Well, the second recommendation was thinking about estimating the answer. And as teachers, we wouldn't just say estimate the answer, we'd give benchmark estimation. For example, I might ask my daughter, so based on that, do you think I ran more than 1 mile or less than 1 mile? And why? And maybe, just rethinking through it, maybe she might realize, well, 5/8, I think that's a little more than half. And so if you did that twice, I guess that's a little more than a mile. And that would be great. That would be great reasoning. I might ask her, do you think I ran more than 2 miles or less than 2 miles? And she might say, well, each of them are less than a mile, so you didn't run more than 2. Well, that's great. So we know we ran between 1 and 2 miles. And that would be an excellent place to start thinking conceptually about that question. And the third thing was to explore using models. So let's do that. Let's suppose that this represents a mile in this case. So there's our whole, always define our whole. And if we're going to look at 5/8 plus 5/8, what we might do is here's the first 5/8 right there. And that might be my Monday workout right there. I'm going to go ahead and do my second Monday workout right here. And let's just think what this looks like. So if I want to compare this to a mile, I can say, okay, here is my Monday workout again. I can put that in here, and there's my first 5/8. That's Monday. And let's go to Tuesday. And Tuesday, I ran these other 5/8 of a mile here. All right. So, yep, it's definitely more than a mile. Definitely less than 2 miles. If I look at it, definitely way less than 2 miles. So I see here that I ran 1 full mile, and then there's 2 of the eighths left over. Yeah, so I guess I ran 1 mile and 2/8. That'd be great. And if we wanted, we could even ask, I wonder if there's another fraction that equals 2/8. And sure enough, yeah, we could even see that's the same as 1 1/4. So I ran 1 2/8 miles or 1 1/4 miles, which is great. And that would be a correct visual model for the question. Now, to Think about it though, the last suggestion was to address misconceptions explicitly, so let's just address it. Let's think. So when we think of 5/8 plus 5/8, we might even talk about a common misconception that students often have is they think they might want to add the numerators and add the denominators. And at first glance, I guess I could see why we might think that, but let's see if it makes sense. If I ran 5/8 of a mile on Monday and 5/8 on Tuesday, would my total be 10/16? Well, let's think about that. 10/16, well, that's less than a mile. We just saw that I ran more than a mile. It doesn't work this way, so it didn't work as we thought. Instead, what we saw was that when we added 5/8 plus 5/8, we were counting up how many eighths we had. And look at this back here. And back here, I can just see down here, I had 10 of these eighths pieces. So when we're adding fractions, that is what is happening. We're saying that altogether, I have 10 of those eighths. Like that. So that's why we keep the denominator the same, because that's the piece that we were adding, right? So the piece we're adding doesn't change. So we're keeping it as eighths, and the top was how many of those pieces we had. And we saw that that was the same as 1 2/8 miles, or even 1 1/4 miles. These were all the same as how we look at it. Well, good. So that's what it looks like to go through those 4 steps by that National Report on Fractions. All right. Well, let's keep moving on here. Now, I just used a word problem with miles, and when thinking about contextual problems, there's all sorts of contexts that work well with fractions, and more than just pizzas. I know we tend to go to pizzas right away because it works, and that's fine. Pizzas, especially for circle models, pizzas are good, but please write some of these down, because I ask you to write some problems with fractions. Think about some other contexts besides pizza. And often rectangles can be easier to partition than circles anyway, so we might have other food like brownies or lasagna, Pop-Tarts, tofu squares, whatever it may be. And I also like to use gardens or lawns with non-food thing. Gardens works really well. Time can work well, because we can talk about fractions of an hour or fractions of a day. For length, miles, ribbons, kilometers, just a foot of ribbon to go through a yard of ribbon. Pounds and tons work well, 5/8 of a pound of cheese plus 5/8 of a pound of dough, how much total weight is the recipe. And we talk about cups and gallons and tanks, all these things work well. And so let's just try and use lots of context when we're thinking about our fraction word problems. Now, I use fraction tiles in the last page with the example, but there's many great virtual manipulatives out there. And I'm recommending a few here that you might use for fraction tiles, pattern blocks, fraction circles, number lines, Cuisenaire rods. So here are some key ones, and there's more than these out there, but here's some I might recommend. So feel free to, write those down or to put them in your saved links there, because that might be helpful as we move forward. I'll encourage you to use those going forward here. So pause, get those down, and here we go. So let's jump in and just do a little more like adding fractions with like denominators, which we just did with the 5/8 plus 5/8 example. But let's have you try for a second. Take 5/6 plus 2/6, and why don't you pause for a second? What would be a story problem you would write for 5/6 plus 2/6? And what would it look like solving it with manipulatives? Try it out. Pause it for a second and see what you think. So before we look at the example, just to make a note, what we're doing now comes in the 4th grade of the Common Core Standards. We see below it says solve word problems involving addition and subtraction of fractions, referring to the same whole and having like denominators by using visual fraction models and equations to represent the problem. So if you're wondering what grade level we're in, this is typically a 4th grade standard. Well, here's one possible word problem I made up. So Adam put 5/6 of a cup of milk into the dough mix. It was still too dry, so he added 2/6 of a cup more. How many total cups of milk did he use? Right, and so now again, we have a context. And again, I might use estimation again. So do you think Adam used more than a cup of milk or less than a cup of milk? Did he use more than 2 or less than 2? And just gets us thinking about the problem a bit more before we start trying to solve it. Now, a key thing here with wording, and you think about your question as well, is when writing fraction, addition, or subtraction problems, it's very important to represent, to know that the whole, we must have our fractions be of the same whole. So in this case, when I wrote that problem, I was careful so that 5/6 was of a cup of milk, and the 2/6 was of a cup of milk, and the question's asking how many total cups of milk. If you see that, that is how fraction, addition, and subtraction works. It must be of the same whole for all the answers. And we'll see that that's different for multiplication and division. So big idea, big down. I'm going to just really note this. In fraction, addition, and subtraction, all three of these fractions are of the same whole. In this case, for me, it was a cup of milk. So let's take a look at visually here, this 5, 6 plus 2, 6 again. Again, with the idea of iteration, if our whole is one whole circle, let's use a circle model this time. For this whole circle, it would be 1 cup of milk. It might look like this, right? And we could do this a lot of different ways, but this is literally what 5, 6 plus 2, 6 looks like. And if I put those together, I could make one whole circle with one of the 6 left over. So I know together I have 7 of these pieces. The answer is 7/6. But also I could put it together and see it's the same as one whole cup of milk with 1/6 left over. Yeah. And that's where we get this interesting idea of iterating with fractions again. 5, 6 plus 2, 6 is 7/6. In words, it looks like on the left, and it's neat to see that in comparison with what it looks like on the right. And again, of course, we don't have 12ths. We wouldn't want to add the denominators. That wouldn't be true. We don't have 7/12ths. We have 7 of the 6th. So again, that's why we don't change that denominator. A big idea here is when fraction addition is we're adding the same size pieces, right? We have to add, these are 6th with 6th. That's a hard word to say, by the way, a lot over again. But we're adding the same sized pieces. Very big idea. And we could do that same problem with a length model, for example. For example, if we wanted to look at the 5, 6 plus 2, 6, maybe in terms of running a mile again, or walking a mile, we could have a number line, and if we break it up by sixths, we could, again, use jumping and hopping on a number line to look at it. For example, maybe the first day I did 5/6 of a mile, so I just jumped 5 spots and then 2/6 of a mile. And a number line, we can see where I am. Altogether, that's 7/6, or 1 1/6 of a mile. So again, different models can be different ways of representing these fraction ideas. Now again, we could address misconceptions, and maybe Adam on his paper said, well, maybe walk by, we see Aaron made a mistake and said 7/12 again. How might we realize that 7/12 is not sensible for this problem? What are some ways to think about why 7/12 isn't sensible? One way to think about it is, again, going back to the idea that 7/12, we think about fraction reasoning, that's just a little more than a half. And 5/6, that's already really close to 1. So how could I take 5/6 plus something else and get something smaller? That doesn't work. 7/12 would be smaller than 5/6, so I just know the answer isn't sensible. So again, focusing on fraction reasoning and sense making helps us know that, again, that doesn't really make sense. We need to go back and think what we're actually doing here and why the answer would be 7/6, not 7/12. So let's start talking about fractions with unlike denominators. So maybe pause the video for a second again and consider, what would you consider a word problem to be for 2/3 plus 1/2? And I encourage you to go to the fraction manipulative websites and try one out. How might you model 2/3 plus 1/2? And what would that look like? So here's one example of a problem. We could say Sahar had 2/3 pounds of trail mix, and Brad had 1/2 of a pound of the mix. How many total pounds do they have together? Again, in your problem you wrote, check to see if this is true. I have the same whole for each of my fractions. 2/3 of a pound, 1/2 of a pound, how many total pounds? There's that parallel structure that's always true in fraction addition. And again, we could do some estimation here. Do they have more than a pound of trail mix or less than a pound of trail mix? And let's take a look again at, with unlike denominators, how we need to think about this. This one's a little different because if we visualize it, obviously we're starting with different size pieces. And that's where the visual comes into play. I mean, how can we add these up if they're different size pieces? Well, it sure would help if we had the same size pieces, if we were dealing with the same size chunks. Hey, so maybe we could do that. Couldn't we maybe find a smaller piece that would go nicely into these, just to find equivalent fractions that would work? Yeah, let's try it out. Let's see if that works. In fact, if we played a little bit or thought about it, we could even just visually kind of explore. But we can see that, for example, it takes 2 of the 6th pieces to equal 1/3, and it takes 3 of the 6th pieces to equal 1/2. So this is the same problem. We just changed it though. Instead of before, as we saw the 2/3 plus 1/2, it's the same problem as 4/6 plus 3/6. We just changed it. So we started with that. We traded in for smaller pieces so that we were dealing with the same size pieces. We wrote equivalent fractions. And when we look at the visual, we see again that when we add them up, we just get 7 of those pieces. We get 7 of the 6ths. So again, with Uncommon denominators, really the idea is, well, that's why we need a common denominator. We'd like to be working with the same size pieces so that we can just, figure out how many total of those pieces we have. So that is, what we're looking at with those. Yeah. With that last one again, with unlike denominators, students may still fall into the same trap of maybe saying 3/5. And again, if we think about why this isn't reasonable, again, we might think about just ways to do that. So why don't you pause for a second and think, how would you answer a student, again, that just threw out the answer 3/5 without stopping to think about it? Yeah, so maybe again, we realize with models or pictures that 2/3 plus 1/2 is definitely more than 1 because we know 2/3 is more than a half. So if I add that to another half, I'm getting more than 1. And 3/5 is less than 1. So again, that can't be true. I can't, that doesn't work. So again, it just goes to show that, it doesn't work, as just adding across is not going to be sensible. It doesn't give us an answer that makes sense here. And by the way, when we're talking about fractions with unlike denominators like this, typically we're now talking a 5th grade standard. And you can see below where it just says we're going to solve word problems using addition and subtraction of fractions referring to the same whole, including cases of unlike denominators by using visual fraction models or equations. And then it even goes as far to say, use benchmark fractions and number sense of fractions to estimate mentally and assess the reasonableness of answers. That's exactly what we were just doing, benchmarking using reasoning as the answer makes sense, and it's that kind of reasoning the standards are calling for in 5th grade. Now, tying into some earlier lessons, just like we had different types of meanings for addition and subtraction with whole numbers, the same apply to fractions. We could have separate, join, compare, and part whole problems as we look at it. So for example, with subtraction, I might think about, how I might word it with comparison, because if we want to do a separate or takeaway problem, we might say something like this. Adam had 3/4 of a pound of flour, right? He used 5/8 of a pound for his muffins. How many pounds of flour does he have left, right? And that would be a takeaway or separate problem. What would it be with a comparison structure? Maybe it could be like this. Adam had 3/4 of a pound of flour. His chef competition, Kirsten, had 5/8 of a pound of flour. How much more flour did he have? I know not the most exciting problem, but it's the idea again. The structures still play in there, and we can use different structures to ask the problems in different ways using those structures. Yeah. So let's talk about, as we move towards some different ways of thinking about unlike denominators, especially, if we don't have manipulatives for everything and visuals, some other ways to draw it out. So we're going to look at a kind of a concrete analogy and a nice visual way that works for unlike denominators, but does so in a conceptual manner and tries to help visualize what's happening here. And we're going to use a little lasagna pan analogy. So I'm going to pull up my document camera again, and let's take a look here, okay? So let's suppose we had a party, and at that party, we baked 2 large lasagnas, all right? Yum. And they were full lasagnas at the beginning of the party. But at the end of the party, this one here only had, it had 3/4 left. So I guess this one didn't get as much eaten as we would have thought. But let's go ahead, I'm just going to shade it in to give it some color here. All right, so this one has 3/4 of the lasagna left. And this one over here has 1/3 left. But with this is a structured kind of algorithm way of drawing, so we need to approach this in a certain way, and I'll explain why. But I always want you to cut the second one going the other direction. So if the first one was vertical, the second one's horizontal. And I want to show here that this one represents, again, we have 1/3 of the lasagna left. So the question is, how much total lasagna do we have left? If we put those together, do we have more than a whole lasagna pan? Less than a whole? Well, let's do that. Well, first of all, again, we have to acknowledge that these are different pieces. These are 4ths, that's a 1/3. Again, with different pieces, it's hard to add those up. We like to have it the same size pieces. So to get it the same size pieces, what we can do is apply the cuts of one lasagna to the other, and by doing it both ways, we should get the same size pieces. For example, this one was cut twice this way. So I'm going to cut this one twice that way. This one was cut 3 times vertically. So I'm going to cut this one 3 times vertically. And now look, the lasagnas now have the same size pieces. And now each one is cut into 12 pieces. This one here, well, 9 of the 12 pieces are left, and this one here, 4 of the 12 pieces are left. Well, interesting. So again, if we want to see how much lasagna is left, we know now we're adding twelfths. And so if we add those up, there's 13 pieces altogether, and those pieces are twelfths. We could even visually kind of move those over and realize that would give us one full lasagna with 1/12 of the other pan left over. And our whole here would be pans. 1 and 1/12 pans of lasagna are left over. And this is just a visual kind of representation of one way of getting common denominators in a visual sense. So let's take a look at one more. Can you try this one? Why don't you go ahead for a second, pause the video, and see if you can repeat what I just did, but do it looking at 2/3 plus 3/5. So pause and try and repeat what I did, and then we'll check and see if you were right. All right, well, let's check your work and see how you did. So again, if we want to use the lasagna analogy, this time at the end of the party, this lasagna over here had 2/3 of the pan was left. So I'm going to go ahead and shade in that 2/3. These people are just not hungry. All right, and then this other pan over here, there was 3/5 left. And one key thing here as well, just a note, it's important to draw these two the same size. When we add fractions, we're, again, assuming it's of the same whole. So if we have two pans, it's very important to realize that these are the same size pans. Maybe I should emphasize that more in the beginning. So we're always adding things of the same whole, as we emphasized earlier. And so if I split this one into fifths, it might look like that. And if 3/5 were left, I can go ahead and shade in 3 of those fifths. And again, these are different pieces, different size pieces. So let's, again, work on cutting these up so we get the same size pieces. So that means over here we could cut this one into fifths that way. And this one here, I'm going to cut into thirds that way. Now, the two lasagna pans have the exact same number of pieces and same size pieces, which makes it, that's the way we're supposed to do it. So now we see there's 15 pieces. Over here, there's 10. Right, and over here, we see that there's 9. And again, if we add those up, we're seeing that we're counting 15ths. Altogether, there are now 19 pieces, and those pieces all represent a 15th of the lasagna. And again, we could even move them over if we wanted and think about it, and that would be one whole lasagna with 4/15 of the other pan left. So we have 1 and 4/15 pans. And again, going back to that view earlier, you know, what we really did here is we just multiplied by a giant 1, right? On that pan, we multiplied 2/3 by a giant 1, 5/5. And that's what gave us 10/15. Oops. And for the other one, the 3/5, I multiplied by the giant 1 of 3/3. And again, that gave me 9/15. And again, we know that 9/15 is equivalent to 3/5 because we just multiply it by a fancy form of 1. Anything times 1 is itself. So those two, you know, these two are the same as these two. So again, this visual method here, obviously if you deal with large denominators, it won't be friendly if you get really huge numbers. But, you know, with numbers, you know, up to 6, 8, maybe, you know, you can work with there and get this. Will it give you the lowest common denominator all the times? No, it won't. But again, that's not important. It may be the most efficient, but any size common denominator will still give us the same answer. We just may have to simplify in the end if that's what is being asked for. All right, so online, if we look at, you know, when you look at teacher blogs, I found a teacher that was talking about how she does this with her class, and she, you know, she made this is a little algorithm. There's a step to this, and here's an example of a poster she had in her room that just helped her students think about, you know, just the 4 main steps to go about it, and you can review that and see it's what we just did. I just wanted to show you a classroom artifact of how a teacher was helping her students just, you know, practice this method here of going through and thinking about it. All right. Now, does it work for subtraction? Well, sure. Yeah, we could do the same thing with subtraction for sure. If we look at 2/3 minus 1/4, let me just go ahead and bring back over the document camera. And if we look at it, yeah, it's definitely the same. Now the lasagna analogy, the wording gets a little bit trickier at first if you are doing subtraction, just because if we say, for example, I had 2/3 of lasagna and I'm taking away a fourth, the model doesn't quite show that as well. The model works really well for the story of adding two things together, but when we look at it different, it's a little bit trickier, but there's a different way to word it that actually goes along better, and let me show you that. So first of all, let's just shade in what we've got. We've got 2/3 of this lasagna and 1/4 of this one. And so first of all, if we're just going to subtract without a story, well, it works the exact same. You know, what I'm going to do is, first of all, these are different size pieces. So I'm going to apply the cuts of each one to the other. And this one here, it looks like now that we all have 12ths in each of these, this one becomes 8/12, and this one becomes 3/12. And if I'm subtracting, I would need to take away 3 from the 8/12, right? And if I take away 3 of those, I'd be left with 5/12. If I take away, those 3, I'd be left with 5/12. And that works. Now, there's lots of ways we could word this, but instead of a takeaway problem, which again, it's not bad, it still works, but may make more sense to have a comparison problem. For example, maybe I had 2/3 of my lasagna left over, and Kirsten had 1/4 of her lasagna left over. And again, we're assuming they started with the same size lasagnas. Now, how much more lasagna did Adam have? That makes sense, because this is Adam lasagna, that's Kirsten lasagna. We want to know the difference. And when we subtract it, we see that Adam has 5 more 12ths of lasagna than Kirsten had. So comparison can be a nice structure that fits well with this model. Other ones work too, but that one is a friendly wording to go with that problem. Yeah, great. So now when wording fraction addition problems, again, as we're teaching, we're going to use curriculum and it's going to have things worded correctly, I hope. But as we find materials, sometimes it may not be. And also, if we're going to make up our own problems to work with students, it's good to think about that you have to be careful when wording these problems. Otherwise, it changes the meaning. For example, I'd like you to look at this question on the stage, on the slide, and decide if this problem is worded correctly for an addition or subtraction problem. And if not, what would need to be revised? So pause for a moment and think about this question and see if you think it's okay. All right, so with that one, let's take a look. This actually is not okay. I mean, it's a valid question. We could solve this, but this is not fraction addition or subtraction. And we know because the first one is 2/3 of a pot of coffee. And Lisa drank 1/6 of the remaining coffee. We said earlier, it's important that you have to have the same whole. 2/3 of a pot is different than 1/6 of the remaining coffee in the pot. It would be correct if they were each of a pot, but they're not here. This is a different question. We could solve this, but it is a different question. So here, to correct it, we might say something like, Carrie drank 2/3 of a pot of coffee. Lisa drank 1/6 of a pot of coffee. How much total coffee did they drink together, or how many coffee pots did they drink together? Just something that in the end, our whole will represent, how much of a coffee pot they drank together. So each fraction must be of the same whole. How about this one? Read this one for a second. Is this one a valid wording? So pause and think about it. All right. What do you think? Is it valid? Well, with this one, it's valid, but we can improve it a little bit. It is valid because we are basically doing a subtraction problem here. We just want to make sure that the answer is in terms of a bottle, right? It's because Juan drank 2/3 of a Gatorade bottle. We're assuming they have the same size bottle. Stephanie drank 5/8 of her bottle. How much more of a bottle does Stephanie drink? So as long as our final answer is in terms of a bottle, it's going to work. So the first wording isn't horrible. It's just we want to make sure that it's of a bottle in the end. How about this one? All right, pause the video again. See if you can think about this one. All right, if you said this one needs to be corrected, you are correct. Well, what's wrong with this one? Well, again, the first one says Giselle had 1.5 pounds of chocolate. The second one said Monica bought 3/4 of Giselle's chocolate. I mean, you could do that, but that would actually be a multiplication problem, not addition problem. We want to make sure that Monica bought also just 3/4 of a pound of chocolate, so that each of them are of pounds of chocolate. And that's, again, with fraction, addition, subtraction, that must be true. So what if we extend it to some other things, like mixed fractions, or fractions that get a little more messier as we go through? How would you approach these? Again, I encourage you to pause the video and think for a second about, what are some ways to think about problems like these? What are ways to approach it? Could we still use visuals? Would we go to algorithms? What are some ways we'd go about to do this? So why don't you pause for a moment and maybe think about that, and then we'll take a look at a few ideas together. All right, well, let's take a look at these together. Again, lots of ways we could do these. So let's just start with 2 1/4 minus 1 1/2. Well, to begin, if we want to start with a story context of some kind, again, we could have lots of different things here. We could say, for example, maybe there was 2 1/4 pounds of butter in the fridge, and we used 1 1/2 to bake a cake. How much butter is left. So let's start with a visual context to begin something like this. So let's start with 2 1/4 pounds of butter in the fridge. So we'll define that to be our whole. One of these rectangles would be a pound of butter. And so I'm going to go ahead and just show what threefold would look like. But obviously in this one, we'd only have a fourth. So there would be my 2 1/4 pounds of butter. Well, visually, we can just go ahead and think about the subtraction here. If we need to take away and use 1 1/2, there's lots of ways to do this. For example here, we could use that as one of our full pounds, and maybe this one we could divide and use that, and we've used 1 1/2. So how much is left? Well, I have a half and a fourth. Well, again, these are different size pieces, so that is correct, but if we wanted to make them into the same size pieces, we could divide this one. So these are now fourths of a pound as well, and we can see I'd have 3/4 pounds of butter left for the future. And so the visuals still work, and there's different ways to think about partitioning and going through. But length models can also be a nice way to see this as well. So let's just take a look at a length model. So let's say I have 0, 1, 2, 3, and again, 2 1/4, well, right now I need fourths on my number line. So just like we partitioned a shape into fourths, we can partition a number line into fourths. So we get 4 equal segments on each one. And so that would be a good place to start. It's just the same type of partitioning as we did up here, just a little different here. And so here, if we have 2 1/4 pounds of butter here, I need to take away 1 1/2. Again, lots of strategies here, but I could just start by maybe jumping back. Well, 1 full pound of butter would be 4 of these. So 1, 2, 3, 4. That would be 1 pound of butter. And I know half would be 2 of these. So if I jump back 2 more, that would be where I'm at. And that's 1/4, 2/4, 3/4 going through. So again, we can see we have area model, length model. And just to go back to the idea of structure of a problem, with a length model, if we had changed the story context to something that was a comparison model instead of a takeaway model, it might look something like this. Maybe we could say Adam ran 2 1/4 miles today, and Anna only ran 1 1/2 miles today. How many more miles did Adam run? Now, it's interesting to think that with models, depending on the story context like that, again, the model looks a little different. So for example here, if Adam ran 2 1/4, I would be right there. But this time, instead of taking away 1 1/2, we just know that's where Anna was. Anna ran 1 1/2 miles right there. And so it's a little different that now we're looking for the difference in a comparison problem. So we see here the difference is, well, 3 of these segments, which are all fourths. So 1/4, 2/4, 3/4. The difference between them is 3/4. So again, we see a separate or takeaway model and a length model here. And of course, these problems can be done with algorithms as well. And if we take a look at that, we have many ways to do it. We might see something like this. Sometimes we see in school students look at, just looking at it in terms of a subtraction problem, lining it up vertically, but it doesn't have to be. But again, if we're going to subtract this way, we realize again, like before, that we have different size pieces, fourths and halves. So we need to get the same size pieces. So, well, we need to multiply by that giant 1 again. So down here, I could multiply that one by 2 over 2. So let's just think, okay, so that would give me 2 1/4 minus 1 and 2/4, which is still 1.5, and now I have same size pieces or common denominators, but I can't take away 2/4 from 1/4, so I have to do a trade. And just like before with just whole numbers, when we trade in, it's about trading in a larger piece for smaller pieces. In this case, I need more fourths, so I can trade in a whole. If I trade in one of my wholes, I'd have one left. If I trade in a whole, I trade in for 4/4, so I get to put 4 more fourths on here. So if I put 4 more fourths on here, that would give me a total of 5/4. Again, same number, equivalent, but rewriting, and I could subtract. Now, if I have 5 of those minus 2 of those, I have 3 of those, and the 1 minus 1 is 0. So I get the same answer. But again, we can see how in this case, in a problem like this, I mean, some of the visual methods actually are even more efficient in ways than the algorithm going through. But all are helpful and all are valid. Good. So let's take a look at one last one before we end this video. And let's take a look at one where it may be a little harder to draw visuals. You know, if we're dealing with sixths and ninths, we could try number lines, but to make these common, it's going to be a lot of partitioning. We could try that lasagna pan method, but again, it's going to end up with quite a lot of pieces. It could be 54 pieces going through, so it's possible. But again, with models, at some point when you get to larger numbers like these, that's where it's where the need for algorithms and other ways of doing it are definitely important, because it gets just inefficient to try and draw things out. But again, to read a big idea, that's why we start with some smaller, more friendly numbers to build the conceptual understanding. And from that conceptual understanding with pictures and models, then we yield to other methods like algorithms that can be used on all problems, and especially ones that are a little more messy. So first of all, one like this, just some thoughts again, is first of all, if we have 1 and 1/6 plus 8/9, well, the main thing here is we really need to think about the 1/6 and the 8/9. We could deal with the 1 right now or just save it for later. That's up to us. For now, let's just go ahead and change these both into fractions bigger than 1 so that they're both not, this isn't a mixed number. And again, changing this to a mixed number, you probably have the algorithm. Oh, you take 1 times 6 and add 1, and that's 7, which is true, but let's think about why that is. Because let's think, well, that 1 right there, if we think about it, if a circle is our whole, didn't draw my picture very well, but let's just pretend that's a whole. So that whole would be 6/6, and this 1/6 of a circle would be something like that. So when we're putting these together, of course, there's going to be 7/6. So when you multiply 1 times 6, you're basically just saying that's the amount of pieces in a whole. You're adding the 1 extra. So that one would be 7/6 plus 8/9. And again, we need to think about getting these to be same size pieces. And that's where, again, you don't have to get the least common denominator, but it can save work later. So we might think, is there a number that we could change these both into that have a common multiple? And sure, we might think of 18. So in this case, to make that one 18, I'm going to multiply by a giant 1. Over here, that's friendly, 2 over 2. And over here, this one I might multiply by 3 over 3. And as we compute that out, we're now dealing with 18ths. So when we add up the number of 18ths we have, looks like that's a total of 37 18ths. So the last step is to simplify here and just think what that number means. And again, our whole is defined by having 18 pieces. So how many wholes can we make out of 37? Well, one whole is 18. 2 wholes would be 36. Oh, I can make 2 wholes. But if I make 36, how many pieces are left over? Well, there's 1 left to get to 37, so I'd have 1 other piece left there. And so again, just thinking through, talking through with you, just some different ways to verbalize it going through, we can see just some different methods and ways of thinking about some different types of fraction problems. So to end the video here, let's go back to where we started. So I think a big idea from this video is when dealing with fraction, addition, and subtraction, just remember those big ideas. We want to think about helping students connect a little better just using contextual story problems that give us something to sink our teeth into. It's helpful to estimate the answer. Again, do you think this will be more than a half, less than a half, more than 2, less than 2? Questions like that are very helpful to make sure we're thinking, actually thinking about the meaning of the numbers and not just jumping into rules. Again, explore using models and visuals to build that conceptual understanding for sense making, and then connect those models to algorithms to see why those make sense and why they work the way they do. And again, there's lots of common misconceptions with fractions, so address them explicitly. Actually talk about them. talk about, bring them up, have students, see why they don't work and why that makes sense and why the correct conceptions hold true. So with that, that ends our video today. And until next time, have a good one.